In this lecture, we're going to talk about timing channels. So remember in the last lecture, we talked about various forms of modulation. And timing channels were one of them. We're gonna spend some time focusing on timing channels because they are one of the more flexible kinds of modulation. And it'll help us understand a little bit of things like absorbing receivers. So when we talk about timing channels, this isn't always true. You can certainly derive a timing channel framework with a non-absorbing receiver, but in this course, we're going to talk about absorbing receivers. And basically what that means is that, remember, we have our region R, our molecule, performing its random walk until it arrives at the receiver. And once it arrives on the surface, the molecule is absorbed on the surface of the receiver R on arrival. Again, I want to emphasize this isn't the only way to do a timing channel, but it will simplify the analysis for us. You can certainly set it up a different way if you want. What we're going to do is we're going to talk about what are called the basic assumptions. For timing channels. And there are really three of them, and they make sense in terms of the way we've already set up the channel, but it'll help us in the future if we make them formal and write them down right now. So firstly, we're going to say the transmitter perfectly controls position and release time of the molecule. Actually, I'm going to call this assumption 1. So in other words, if you think about how the transmitter works, this basically means the transmitter works perfectly. Second, the receiver perfectly measures the arrival time and position of the molecule on its first arrival. In R. So again, this assumption basically means the receiver works perfectly. The receiver's job is to measure the time at which the molecule arrives. We say position here, which doesn't matter. We say position here, which doesn't matter so much for one-dimensional receivers, but it might matter for higher dimensions. And thirdly, on the first arrival, the receiver absorbs the molecule and removes it from the system. So assumption 3 means once it's arrived, this molecule is done. Its Brownian motion ceases, and it does not, for example, come back later and lead to multiple arrivals. So in other words, you have one release and one arrival. That makes the system much cleaner in the sense that for each release, you have exactly one arrival. But it also turns out that, as we might show later if we have time, it also turns out that assumption is ideal. I can describe that a bit in a moment. So let's talk a little bit about these assumptions. So features of these assumptions. So one is that the Brownian motion, the initial point of the Brownian motion, I'm going to call that B of TR. So TR is the time of release. Is specified. So that works because the transmitter perfectly perfectly controls the time of release and position. So that initial point of the Brownian motion at time TR is specified. And because it's specified, remember, the Markov property implies that if the molecule was propagating before then, we don't care. This splits the statistics of the Brownian motion such that if I know this point, I don't need to know anything that happened before. Secondly, the final point, the Brownian motion BTA is specified, where TA is time of arrival. And thirdly, there is exactly one arrival. Excuse me, actually, let me back up here. That's not quite true. There is at most one. Actually, let me make this a little more specific. There is exactly one arrival time, TA, per release time, TR. Now, I was going to say at most one, but we're going to handle the possibility that it doesn't arrive. We actually will not see this in the example that we deal with, but our mathematical framework can include the possibility that the molecule does not arrive. By setting TA equals infinity. So in other words, the idea that the molecule is removed once it arrives means there is exactly one arrival time. It might not arrive, in which case we just set TA equals infinity. The whole point here, however, is that there is not more than one arrival time. In other words, that scenario that I pointed out a second ago, the molecule doesn't bounce. It doesn't bounce on the receiver and come back more than once. If that were to happen, that would be very difficult to analyze. So we assume that away, but also, now I'm going to hand wave about this, but we might show it formally later if we have time. The fact that the final point BA is specified means that if I know that the molecule arrived, I don't need to know anything further about the molecule, because now the Brownian motion is split between the times before it arrived and the times after it arrived. If I know that it arrived, the Markov property says that observing it further, even if it's not absorbed, gives me no new information. So what does this imply? One thing this implies is that there is a propagation time TA minus TR And I'm going to let that be equal to, let's let that equal Z. I've already used N. I kind of wanted to use N there, but for reasons that will become obvious in a moment, but we're going to call that Z. So there's a propagation time TA minus TR equals Z. And moreover, there is exactly one propagation time per molecule. So you release a molecule, it propagates with propagation time Z, then it arrives. And moreover, this propagation time is the first arrival time. Now, this is why we talked a little bit about first arrival times a couple of lectures ago. It's because they're going to become very important right now that we're talking about timing channels. So consider the following. Or consider a timing modulation scheme. So the transmitter, what's the transmitter's job is to select release times. The transmitter generates a vector of release times. I'm going to call it T1, T2, and so on up to Tn. And the receiver observes, these should be TRs, excuse me. Let me back up. TR1, TR2, so on, TRN. Those will be my release times. My receiver observes arrival times. TA1, TA2, and so on, TAN. Now, recall that each arrival time, or each molecule, has a propagation time. And that's true here of these vectors, because the propagation time is applied element-wise. Because the propagation time is applied element-wise, the propagation time from TR1 to A1, TR2 to TA2, and so on, these will basically, I'm just going to add a vector of propagation times between these two, and basically what I'll get is the vector Z. So TA minus TR vector-wise is Z. So Z will then be Z1, Z2, and so on up to Zn. So this is my vector of propagation times. And if I rearrange this a little bit, what you will see, actually, let me just do this. I'm going to call this star, equation star. Rearranging star, we can see that TA is equal to TR plus Z. In other words, if Z is additive noise, is treated as additive noise, and the release time TR is the signal, then this is an additive noise channel. So in other words, we are very accustomed to dealing with cases where a noisy signal is observed by the transmitted signal plus some additive noise, and that's exactly what we have here in the timing channel. And it's made possible by, firstly, our system assumptions, and secondly, the fact that we're using an absorbing receiver. So that's a nice clean reason to model absorbing receivers. The other issue here is that the distribution of Z is given by the first arrival time distribution. So that's convenient. We have our releases, we have our signal, we have our additive noise. We know what the additive noise distribution is. So we can reuse a lot of the concepts that we're already familiar with for dealing with additive noise channels. There is an issue here though. So let's come back to this way of specifying the problem, and recall that I talked about when we first started talking about modulation schemes, we said, generally speaking, we're talking about indistinct molecules. So we can't tell these apart. So if we release these, we release molecules at these times, and the molecules arrive at these times, which are different. An issue is that the received molecules may arrive in a different order than the transmitted molecules, and there's no really good way to tell that apart if the molecules are indistinguishable. In other words, let's say this is transmitted first, this is transmitted second, but this takes an outrageously long amount of time to arrive, and this arrives very quickly. This one could arrive first, and that one could arrive later. That actually makes a big mess of our additive additive assumption here. We are actually going to ignore that problem. So that is an unsolved problem, and it's a very difficult problem. So, however, the indistinct molecules may mean received, the vector TA is in a different order than the transmitted vector TR. That is a very annoying problem. Like I said, it's unsolved. It might even be unsolvable. Well, I mean, maybe someone clever will come up with a solution, but it actually relies on a computational construct. So basically, the way in which you calculate the probability density function of TR given TA, if they're allowed to rearrange, is there's no, it can be shown there's no fast algorithm that does it other than summing over all the possibilities, or something very similar to it. There is a slightly more clever way, but it's still exponential in complexity, super exponential in complexity. So this is a tough problem, and we're going to avoid it. Because it's tough, we're going to avoid it. So here we will consider molecules one at a time. In other words, we're basically going to consider a universe with exactly one molecule in it. That molecule propagates and it arrives. So for now, let's put aside the question of what happens when we have to repeat molecule transmissions. We're just going to consider molecules one at a time. So in other words, we have TR plus Z equals TA, where all these quantities are scalars. So in other words, we have one molecule, which has one release time. That molecule has a propagation time, and then I add those together to get the arrival time. So one molecule in the entire universe. So I don't have to worry about things arriving out of order. And I don't have to worry about, for instance, scattered molecules coming in from somewhere else. It's just a molecule with a fluid medium and one message-bearing molecule. So in this simple universe, now we can cleanly implement our additive noise assumption. So consider a set of messages. It can be non-binary, but we're going to say TR is in 0 and 1. Just as a binary message, there's two possibilities. So basically what's going on here is that if I want to send a 0, then I release my molecule at 0 seconds. Excuse me, that's not equals. This isn't a vector, this is a set. So what I'm saying is that the release time is taken from the set 0 or 1. What I mean is that send a 0 means TR equals 0. In other words, I release a molecule at 0 seconds. Send a 1, TR equals 1. In other words, I release a molecule at 1 second. We're going to assume an environment without drift. And the receiver, a 1D environment. With the receiver located at distance D from the transmitter. And remember my setup from before, I release at the origin. There's a distance D to the receiver. And when I release, I just drop the molecule in the one-dimensional medium, and the molecule then propagates freely. It can propagate to -infinity if it wants to, but once it arrives at D, then it's absorbed and it's done. So this is additive noise, and what I can say is that, so Z is distributed Levy, and we've talked about this before, with the scale parameter equal to, let me just make sure I'm getting this right. The scale parameter is equal to D over root 2D. So in other words, remember the scale parameter is C, and C squared is equal to D squared over 2D, where D is the diffusion coefficient, capital D, that is the diffusion coefficient. So in any communication system, I have to consider how the receiver works. So consider maximum likelihood detection. And this is just additive noise, so we should be able to easily figure out what's going on here. The maximum likelihood detector, basically what I do is I calculate the PDF of the observable, the arrival time, given that the transmission is 0 and the probability density function of the observable given that the transmitted value was 1. So in other words, I say what I observed given that 0 was sent, what I observed given that 1 was sent, I pick the maximum. So this is the likelihood function as a each of these is the likelihood function as a function of TR. I know what TA is, that's given by the receiver. So this is a function of TR, and basically I pick the value of TR that maximizes this function. That's the maximum likelihood detector. So I can write Z, the distribution of Z, excuse me, because it's additive noise, f of TA given TR is equal to f of Z, that's the Levy distribution, of TA minus TR. So in other words, basically I solve this for Z. I take this and I solve it for Z. And then Z is distributed TA minus TR. And as a Levy distribution, I end up with the square root of C over 2 pi e to the minus, sorry, I'm using the scale parameter. I actually want to use the real parameters. Square root of just let me make sure I'm getting this right. Square root of d squared over 4 pi d e to the minus d squared over 2, excuse me, that should be 4d TA minus TR, all divided by TA minus TR to the 3/2. So the detector will calculate this for TR equals 0 and 1. So in other words, it will do this. So f of TA given TR is 0 is root d squared over 4 pi d e to the minus d squared over 4d TA divided by TA to the 3/2, and f of TA given TR equals 1 will be root d squared over 4 pi d e to the minus d squared over 4d TA minus 1 divided by TA minus 1 to the 3/2. The idea is, in the maximum likelihood detector, you pick whichever one is larger. So if this one is larger, you pick 0. If this one is larger, you pick 1. Also remember, the distribution of Z is 0 if the argument is negative. That means if you receive anything less than 1, these terms will be negative. Well, TA minus TR will be negative. And so that means this would be equal to 0, which means that necessarily if you observe something less than 1, you must pick 0, because it's impossible if you release the molecule at time 1 for it to arrive before time 1. Okay, so the way in which we normally think about communication systems, or like if you have a Gaussian, a Gaussian transmission at -1 and 1, we would normally draw the two probability density functions like this. And we would say, yeah, there's a threshold in the middle. And if I detect anything less than 1, then it's -1. And if I detect anything more than 1, then it's +1. So there's something similar going on here. So the timing detector for the levy distribution will look a bit like this. Starting at 0. So there's 0, sorry, that's 1. The levy distribution will look a little like this. Oops, that actually is badly drawn. Starting at 0 and starting at 1. So everywhere here, so there's where it crosses over. Everywhere to the left of here, so there's like a threshold here. Everything to the left here, I would pick the bit is 0, and everything to the right here, I would pick the bit is 1. So basically, what I'm getting at is that the way in which timing channels work with absorbing receivers is pretty much exactly like how normal communication systems, or the kind of communication systems that we're accustomed to work with additive Gaussian noise. It's just that now it's levy noise. Or if you have drift, then you have inverse Gaussian noise. And in fact, a paper some time ago that I wrote introduced what's called the AIGN channel for additive inverse Gaussian noise. And that's for molecular timing channels with drift set up in exactly this way. I am going to add, as part of the course material, I'm going to add a Jupyter notebook that will let you play around with these. And we'll do things like calculate probability of error. So please look for that.